Now let's look at this case scenario. In order to increase sales, motor vehicle design engineers want to focus their attention on the aspects of the vehicle that are important to customers. For example, how important is fuel efficiency with respect to sales? Now, the motor vehicle design engineers want to focus on the aspect of vehicles that are important to customers when buying vehicles. Now, one of the aspects that is important to customer is the fuel efficiency of a particular car. So they want to know if fuel efficiency there is a relationship between fuel efficiency and the sales of a car. Now, one way to measure this is to compute the correlation between the past sales and fuel efficiency. Is to look at the sales of cars and fuel efficiency in order to see if the past sales of cars depends on the fuel efficiency of the vehicle. Now, used by Bivarate Correlation to measure the importance of fuel efficiency to the sellability of a motor vehicle. Now, we are going to see how we can do this in R and how we can do this in XPSS. Now, this is XPSS. This is a data set in XPSS. We have the various names of the data set, and this is the data view. These are data set. We have the model of the data set, we have the sales of the data set, we have the type of vehicle of the data set. Now, when we go to our variable, when we look at the type of our data set, we have the types of our data set here. We have the automobile represented by 0 and the truck represented by 1. Then also we have the engine size of the vehicle, and we have this represents the MPG, represents the fuel capacity of the vehicle. Let's go to the variable view. You can see the MPG deals with the fuel efficiency of the vehicle. Sorry, not fuel capacity, but rather the fuel efficiency of the vehicle. And also we have the log transformation of this dataset for sales. We have the log transformation for sales and for all other variables. Now, so we want to see how we can actually do this in XPSS and how we can run that in R Studio. So first and foremost, let's run the correlation. We go to analysis. When we click on the analysis menu, we place a mouse pointer on the correlation. On the correlation, we're going to select the Bivarate correlation. Now, this is what we're interested in. And we are interested in those two. We're interested in to see if there's a correlation between the sales of the vehicle in thousand, and also you can also expand this to see more of that, the sales of the vehicle, and also want to see the fuel efficiency represented by MPG to see if there's a correlation. By default, SPSS is going to compute the Pearson correlation. If we want to compute other types of correlation analysis, we'll just simply click any of the checkboxes to check it. Now we click on OK. The moment we click on OK, it tells us that the correlation between the fuel efficiency and the sales of vehicle, between sales and fuel efficiency, is minus 0.012. That is almost 0, and we can see the significance that is not significant. In other words, there is no relationship between the sales of car and the fuel efficiency of the car. It is different from what 0 is. Now, that is what it gives us here. So what can I see if we can, let's do that in R Studio, and let's run that. But before doing this in R Studio, we have to import some packages in R Studio. So we call importing some package with R Studio. We have to install the packages, and you have to use the doc codes. Now we are going to use the read XL and the declare function in this particular exercise. So if you do not install the read XL function that helps you to read the Excel file, in R Studio, you can simply install that. Now I've already installed that I've already installed those packages in my R Studio. So all what I need to do is to activate it, and it's already activated in my App Studio. So that is a read Excel. Now you can see I already have that file. Read the Excel file. So it helps to read the Excel file. So you run this code to activate that, and then you run this code. You run this code to install it. This code install while this code activates it. Now the other thing we need to install is a deploy function. Okay, when I have to install the dplyr function, the dplyr function, that is dplyr function. So recall we have to put in a double quote the dplyr function, and I have to that particular function I have to activate it. Now I've already done that here. You run this code to install it while you run this code to activate the function. I already have the function here. I already have the code here. I already have the code here. I already have the code here, so I can just install that. So the next thing now we have to import our file. Now in order to import your file, first and foremost, let me get my working directory. Now I want to get my working directory. Okay, let me simply click all this so we can work with it. Okay, now this is my working directory. Okay, and I can set this. Okay, that's my working directory. Okay, let me set the working directory. Okay, that is my working directory. This is already where I am working on. So setting the working directory is not necessary, but the file I want to work with is located in this folder on my system. Is located in this folder on my system in my document. Is located in this the file I'm working with is located in this. Look at it, our programming. Once I click on this our program, I want to work with this car sales 4. This is my dataset. Now, now this dataset is located in this folder our programming. So if you are not working on your current working directory, you need to set that by running this code. So I don't need to run this code any longer because I'm already on currently I'm working on that particular directory. So all now we need to do is to import the file into SPSS. So what we need to do is to import the data set into SPSS. So we use the classes for, let's still call it classes for, and then equals to the read. We can use the read underscore Excel. Okay, we can use that, and then we get the classes for. Now you can see we have .xlsl as my extension name. .xl .xlxss as my extension, as my file extension name. Then we run that particular code. Oh, it's telling me this object that is not found. Okay, now if that actually is not found, if that actually is not found, then you run this to set your working directory. Now let's run this code all over again. So it's telling us that this particular that particular object is not found. Okay, now we run that code. It has actually brought it in. Now that is a classes for. Now this when I click on that, now these are the data sets. Now this is the model, this is the sales, and this is the type of the vehicle, and the engine size, and we have the log, the transformation of sales, the log transformation of sales. Also, we can also let me delete all this. Um, not all this. Okay, I'm just deleting all these things. Okay, now this is my data set. We have the model, we have the sales, we have the time, and also we have the MPT, that is the field representing the fuel efficiency, and we have the log transformation of the sales. Okay, now that is my data set. Also, we can import this data set into R by using this order code. I recall my datasets, I've already converted my dataset into an Excel file. I've converted my dataset into an Excel file before saving it. So I converted that into an Excel file before saving it. So I can view my dataset if I want to view it will bring it up in an Excel spreadsheet. So I've converted the dataset into an Excel file before importing it into R Studio. So you convert your dataset into R. Also, I can also make use of this function. It also helps in reading the Excel file, the XLX. It helps in reading the Excel file into the dataset. So we can also run either those code or those code to import your dataset into the Excel spreadsheet. But now it's telling me, oh, part 5C document, this is unable to open. Okay, okay, I'm able to open using this particular code. So now that imports it there. So we also have used the XLXX and not the one without the X. So that is why we had the initial error. So we can either use this code, you can either run this code to import your data, your Excel file into our PSS, or you run this particular code to import your dataset into our PSS. Now I've imported my dataset into our PSS. What I need to do is to look for the correlation. Now, in order for you to look for the correlation, you use the correlation um, function. You type the correlation function, and then we use the cast is for, and we are looking for the correlation between the sales of car and the fuel efficiency represented by the NPGMP. Okay, now this is the system and we run this particular code. Now you can see I have minus 0.022 as the correlation between the fuel efficiency and between the fuel efficiency and the between the fuel efficiency and the sales of car. And when we make use of the expresses, we have minus 0.0, approximately minus 0.02. So you can see we have the negative correlation, but we're using the XPSS and R Studio. Now, this to tell you that there's a negative relationship between the car sales and fuel efficiency. By default, our studio also run the PSC correlation analysis. So this is a PSC correlation analysis. If you want to run other type of correlation analysis, you can look at my video, previous video on how to run other alternative correlation analysis. Nevertheless, we are going to touch that before the end of this particular um, training. So we can see that the correlation between the two datasets, and we can also look at the significance of this correlation between the two datasets. Correlation compute the correlation. compute the correlation test between those two. Okay, now instead of this, we can copy this and paste it here, and we use the test. Now, and we run this, helps us to compute that. Now, running this, we have the same correlation, but when we look at the p-value, you can see that it's not significant. So we arrive at the same decision using the R Studio and the SPSS. In the SPSS, we concluded that the correlation between the fuel efficiency and the sales of car is not significant. In other words, the car manufacturer, in other words, the car design engineers shouldn't focus on the fuel efficiency of car while manufacturing car, because that does not sales does not depend on the fuel efficiency of a car. Now, what customer don't look at the fuel efficiency of a car while buying a car, or making when making their decision about the type of car to buy. So now, but nevertheless, our datasets, nevertheless, when we look at our dataset might be skewed to the right or skewed to the left. In other words, our dataset might be skewed. The Pearson correlation coefficients work better when the dataset is not skewed. In other words, when the dataset is normally well distributed, or when the dataset meets the when the dataset meets the parametric assumption, especially parametric assumption of normality. Additional assumption of normality, and also the dataset has to be an interval scale dataset. But the major assumption is that the dataset must be normally well distributed for we to use a Pearson correlation analysis. So by default, the R Studio and SPSS runs the Pearson correlation analysis. So we can do further diagnosis to check our dataset, to check the nature of our dataset. If the nature of our data set is skewed or not. So we can check if the dataset is skewed to the right. Whether our dataset is skewed to the right or is skewed to the left. Now, in order to do that, we have a particular function in R which is known as Shapiro test. We can use the Shapiro the test, that is the weak normality test, and the weak Shapiro weak normality test. Now we can look at our data set each after the other. We run that. Now you can see we can see the p-value. You can see this is far away from 1, is not closer to 1. We can see that the value, and we can see this p-value. The HO is that our data set is normally what distributed. So we can see that HO is rejected. We can also copy this. We can simply copy this and we paste it. We run that for the NPG. Now when we run that, we can see this is closer to 1, and that means the that of the fuel efficiency is approximately normal distributed. Now we can check this using the scatter plot. Let's see, using the GG plots. Okay, it does a GG plot. Then we can pass in the data. We can pass in the data. Our data is car sales for. Then we can pass in the statistics. The x is equal to the sales, and the Y is equal to MPG, and we could use the geo point, or we could use the geodensity tool, but we want to use the geo point to diagnose this. Okay, now that gives me for the geo point. We could simply run this, and that gives us the scatter plot. But you can see X is MPG is the X, that's the fuel efficiency, Y the sales is the Y. Okay, we can run this now. Now you can see that the outliers in the dataset, this is a 7. We have one outlier here, we have another outlier here. Also, we could also decide to copy this. We could copy this and paste it here, and decide to increase the size. Let's make this 2, and we could make the shape. Now we want that scatter plot. Now that increases the scales. Now you can see that here. That we could also decide to let's see which data point is this and which data point is this. Those two data points are outlier, but remember we are talking about the influence of fuel efficiency on the sales of car. So this particular data point is an outlier, but might not really regard it as an outlier because it's part of the data set in which we are diagnosing, which we are running analysis to. Because you can see it's only the data set that has the high sales, while the fuel efficiency have influence on this particular brand of car. But we cannot really take that into consideration. We can see it as an outlier. So why I'm diagnosing our data set for that, we are going to focus only on this particular data set and exclude this outlier. But for now, let's leave it for now. So let's just copy this and let's try to run that. Now I'm going to do this. What I'm going to use, I'm going to do the geo text. Now under this geo text, I'm going to use the label. Okay, what I'm going to use the label, and the label here we're going to use the model of the car. Now when we go to our data set, you can see the previous model of the car. So I want to know which model of the car. I want to diagnose to see the model of the car that are represented by these points, the outliers in the data set. That is what I want to do. Okay, now I have that to, let me try running that. Object model. Okay, now we can see, oh, sorry. No, no. I'm sorry for that. We want to use the geotext on this text. Let's run a diagnosis on this, and we can see the geotext, that's geo label. Geotext add only text to the plot. Geo label plus a rectangle behind the text. Okay, the mapping is tested the position. Those are the arguments. We have the size legend, the check, the paste. Let's look at the other arguments one after the other. We have much of these arguments here. Okay, semantic padding, radius, label size. Geotext and add static label equals to y and the label. So what we are making an error is this. Um, this is where we make an error. So what we are going to do is this. Okay, now we can see that the outlier is the F series and the metro. But this F series fall within our data points of analysis because we are looking at the influence of fuel efficiency on the sales of car. So we can exclude this particular outlier for now. We can exclude this particular outlier and leave the other outlier for now. So what we're going to do now, let's remove this other outlier, this metro outlier from our dataset. And to do that, let's rename our dataset to houses. Let's call that council 7. And let's have this. Then we add the car sales 4. One of the steps is that we have this and we make and we make use of this function. We make use of that particular function and we have the metro is case sensitive. Okay, we have the metro, comma, and the data set, the name of our data set, and then we pass we could pass the 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 column in which is interested and the comma there. So let's run this particular line of code and let's see. Now, only this particular line of code, we add this. So the moment you click on this line of code, now we are looking at the F. Let's see if it is okay, that is sorting our data in ascending order. If we can find the F, okay, after E, the F series in a dataset. Okay, add the F series in a dataset. Okay, now that's what we are trying to do. So we're trying to see that we're trying to so that F series the metro sorry we're talking about the metro okay that's F series and we can see we are dealing with the metro Now you can see the metro is out from our dataset. The metro is not located in our dataset. Let's see if we have the metro here. In this particular dataset, if we have the metro, so the metro in that particular dataset. Okay, now you can see the metro is in this particular dataset. That is the 4. Why the metro is no longer here. So we've used this particular code to remove the metro. Alternatively, we can use this other code to remove the metro from our dataset. So all we need to do is we could also run this particular code. We could also run this particular code to remove the metro from our dataset. Can run that code to remove the metro from our dataset. So you could also run this particular line of code to remove the metro from the dataset. Okay, now we've already removed this metro from our dataset. Now let's plot that scatter plot all over again, and let's see. But recall, I've given my dataset a new name class is 7. So I'm going to change that to 7 because I don't want it to conflict with other names in the dataset. And I have to change this to 7. Then I'm going to run this dataset all over again. Now you can see that the metro is no longer there. I don't have the metro any longer. So that is the dataset we are having here. Now, what we're going to see now, we've excluded the F we've excluded the metro from our dataset. So we could do that in XPSS. In XPSS, we could just go to the data and then we do select case. Now, it brings up the select case dialog box. In the select case dialog, we are going to select the select if condition is satisfied. If then we click on this model is this, and we are going to type the metro. Remember, it's case sensitive on the metro. And we click on continue and click on OK. And when we click on continue, click on OK. Now we've excluded that from our dataset. Now what we're going to do now, we're going to plot the chart. We're going to go to the chart, and we're going to see the scattergram. Okay, before we remove this from our dataset, let's see the scattergram first and foremost. Okay, let's see the scattergram how it looks like before we remove that. Okay, this is my scattergram. I want to do the scatter plot. I need the fuel efficiency of the car and the sales. And the sales is a y variable. Y the fuel efficiency of the car is my x variable. Now that gives me this, and let me plot that and let's see. Now you can see the dataset, and let me recall that. Okay, now let's go to element properties. The statistics by calling the name. Okay. The variable is sales 8,000, and the statistics the value. Okay, let's look at the basic elements. The group, the title, what what I'm actually looking for, I can get. What I'm actually looking for, I'm looking for. I'm coming please. There's something I'm actually trying to get. Trying to recall where it is located. Okay. Now, what we're going to do now is we go to the group and point ID label, and we pick the model, click on OK. Now that gives me the scatter plot with the name of the variables. Now you can see the metro. Now to remove the metro in SPSS, we go to the data menu and you click on select cases, and you go if condition is satisfied, and we click on this, and this we just repeat what we did. The metro record is case sensitive, and we click on continue, and we click on OK. Now that will remove the metro from the scatter plot. So let's go back to our chart builder, and we go to the graph, we go to the chart builder, and run this chart all over again. Now you can see it removes them from the scatter plot. It removed the metro from the scatter plot. The metro is not part of the scatter plot. So now the metro is not part of the scatter plot. We can now run the analysis. We can now run this analysis of data set. Now, what we're going to do, we're going to run the correlation analysis using the metro and using the log transformation. Now, we've seen that our scatter plot is a data set is not normally distributed. Since a data set is not normally distributed, to get a good estimate for a data set, we have to transform our data set by using the log transformation of our data set. So let's quickly do that in SPSS. First and foremost, we go to analysis in SPSS, and we can simply recall the analysis we did here. We recall the last analysis, but this time around we are not using the we're not using the sales, the normal sales, but rather we are using the log transformation for the sales. Now, this is the log transformation, the internal log transformation for the sales. So it has already been transformed in a data set, so we don't need to do any other thing. By default, XPSS compute the Pearson correlation of analysis, then we click on OK. When we click on OK, that gives us a better estimate. You can see we have approximately we have 0.136, but still yet is not significant. Okay, let's see how we run that in this. Now we're going to run the correlation coefficients here. We're going to use that to run the correlation analysis. Or we can see, okay, let's just, well, recall this time around we are using class sales 7, and we introduced a data set. Now this time around we are using the MPG and the fuel efficiency. Okay, first and foremost, let's use them. No, okay, and the sales. Okay, now let's use the log transformation here. Yes, instead of using what is in a dataset, recall a dataset and already may transform the log transformation is already done in a dataset. What we have is 0.053, and that's the that a dataset. That is what we're having 0.05. Okay, let's copy this and then let's use the log transformation in the dataset. Now, in the dataset, we already have the log transformation of the sales of car in our dataset. Now in our data set, we already have the log transformation. Now that's the log transformation in our data set. Let's run this. Now both gives us the same statistics. Okay, let's see what we got using the SPSS. The flow efficiency and the log transformation of our data set, and we click on OK. I want to compare this here, what we got. Initially, we got this, okay? Then we'll exclude that particular data set. In SPSS, we have this. We excluded the data set, we have this in SPSS. Okay, let's go to the R Studio and let's confirm. In the R Studio, we have 156 observation in SPSS. Let's see, that is R Studio in SPSS. Let's see how many observation we have. Okay, in SPSS, they make use of 153 observation in SPSS after removing the metro. But after removing the metro, log transformation for sales is 156. Fuel efficiency 153, log transformation 153. Log transformation sales. Okay, for sales is 156. Now for fuel efficiency is 153. Okay, for fuel efficiency is 153. Okay, so that's where we're having a problem with the data sets there. That is where we have here we have 156. So but in XPSS the fuel efficiency we have the 153 in that particular data set. So we can still work on the data set to reduce that to 153, but instead of going through that, let's rather look at the group dataset. Now, let's go through this analysis. Now, you can see based on this, um, there is a positive relationship between the two datasets, between fuel efficiency and the sales of vehicle, but this positive relationship is not significant. And we can do more diagnosis on that dataset. Since our dataset, when we look at our dataset, we have two types of vehicle. Here also is giving us a positive correlation between the two datasets. And if we want to test for that, if we want to test for that, if we want to test for that, if that relationship is significant, now you can see that the p-value is greater than 1% and is greater than 10%. So both gives us positive relationship and tells us that it's not significant. Now we have to do more that we can do more diagnosis in our data set by looking at our data set all over again. We go to our data set. When we look at the variable view, we can see that in the model of our data set, when we go to the vehicle type of our data set. Now we look at the data set by vehicle type. We look at the types of vehicle in our data set here. We have automobile and we have the truck. We have automobile and we have the truck. Now what does this tell us? That makes tell you that the reason people buys normal car is different from the reason people buy the truck. So the reasons are different. So combining both together might not really give us a proper understanding of the relationship between the sales of car and the fuel efficiency of a car. So it's better we separate this data sets. So in order to separate this data set, we can split the data set into two. We can look at the data set by separating it. Let's try splitting that into two. So this brings up the split file dialog box. I want to split it by vehicle. So let's say compare group. Click on vehicle. Now group based on, and we click on OK. Now sort the file by grouping vehicle. Now, so we can now go back to our scatter plot. We can go back to a scatter plot to the graph, or we recall this and then bring out a chart builder. Let's bring out a chart builder dialog box. Now this time around we are removing this. Okay, let's just reset this. We go to the gallery here. But this time around we are making use of the group scatter plot. We are trying to group the dataset now. So, but we are using the sales fuel efficiency, which is the X variable, and we are using the log transformation of our datasets. Now we are looking at based on the variable type, we are controlling it by the variable type, the vehicle type. Now we click on OK. Now this gives us a separate scatter plot for each. Now you can see so let's go back to the chart builder and bring up our chart builder. So we're doing okay, group to statistics. Okay, it's already selected by default. That actually splits the data set. So let's go back to the split and then try to compare this group. So let's run this in XPSS. So what we're going to do, I don't want this. Okay, now in this particular case in XPSS, let's put the minus, and we are going to use in this particular case in XPSS, in R Studio, we are going to use the colon. Let's make that to be type. Okay, let's run this and let's see. Now that gives us the scatter plot. Now you can see the scatter plot. We can see the type here. You can see the type ranging from 0 to 1. Uh, the, the white color represents the automobile, while the dark color represents the truck. We can also still copy this. We could either run that code or rerun this particular code by making this to the color. Okay, we can run that color to the type. Okay, then let's try to put in. Let's see what it will give to us. Let's just try that and see. Let's see what it's going to give to us. Let's see if we are going to run. Okay, that changes the color of the. Okay, now we can make the color to the type. Okay, but if we want to run that separately, just as what we have in XPSS, we could make use of the face wrap if we want to run that. So we could use that. We have to use the type. Let's run this and see. The types are very cool. Of the type not found. What we're going to do here, we need to include. Okay. We need to include this in. Okay, let me simply bring up this. Okay. Okay, let's run this and see. Now that separates the data sets now into two different parts. Now you can see this represents us for the automobile. The zero is for the automobile, while one is for the truck. We'll go to our data set in XPSS. We can see that here that the zero represents the automobile, while one represents a truck. So we can see that from our data set that we can see from our data set. Okay, let's change this to the log transformation. We should be using the log transformation of our dataset here. That's what we should be using here. Let's see. Okay, using the log transformation of the dataset, you can see our dataset is normally distributed. That improves the normality of the dataset. Now fine. Now you can see that improves the normality of the dataset. Unlike why when we plotted that just using the normal scales of the vehicle. Now you can see that when we included the log transformation of the dataset, that actually improves the data sets, that actually improves the data set, that they are all centered on this particular point, that that improves the normality of the data set. So in XPSS here, let's go to XPSS. Let's recall this and let's use the log transformation of the dataset here. And now using the log transformation of the dataset, that gives us the scatter plot there, and the log transformation gives us the scatter plot. So while running analysis on your dataset, we make use of the Pearson correlation of analysis, but the Pearson correlation analysis performs better when your dataset is normally distributed. So once your dataset is not normally distributed, you need to improve your dataset. You need to transform your dataset by introducing the log transformation on your dataset. Then you use a Pearson correlation of analysis, which will improve your dataset, and it will also improve the statistics of your dataset. You'll be able to get the underlying relationship or association between your dataset. So now we've done that. Now we can now compute the coefficients based on the split data. Now, okay, now let's compute the coefficient based on the split data, but let's do that with XPSS first and foremost. Going back to XPSS, let's recall this. Now we've splitted our dataset. Okay, now let's run this based on the split data. Now, wow, based on the split data, you can see that the automobile and the truck XPSS separated the two, the analysis for automobile and that of the truck. And you can see the full efficiency and the sales of very good, the log transformation, that the correlation is fairly strongly correlated. They are fairly strongly correlated. In other words, fuel efficiency is fairly strongly correlated with the sales of the vehicle. And you can see this relationship is significant and positive. But that for truck is telling us that the correlation is strong. It is a positive correlation and it's not strong. It's a very weak positive correlation and it's not significant. That is the correlation between the sales of truck and fuel efficiency. That is no correlation between both of them. That the relationship between the sales of truck and the fuel efficiency is different from zero. So separating the data set, we can have more. We can have more. We can view our data set more. We can have more understanding of the relationship, underlying relationship or association between our data set. Now let's do that under using the XPSS. Now splitting our data set, we have the we are trying to split this data set. We are trying to split this data set. Okay, we are working with this. Let's call that because we are trying to split the data set. Let's say split a well, we are just let's rather let's make this to be split. Let's call the split data. Let's call that the split data. Um, that equals to split data. That is 7. We want to split this data. Okay. Let's try to split the data and run the correlation on each let's split the data, and what we're going to do, we're going to pass the pipe function. Okay, now this pipe function, and we're passing the pipe function. Then we are going to group by, we're going to group by type. We're going to group by type. Then we're going to pass the pipe function again. We're going to pass the pipe function. Then we're going to summarize. Let's call this let's just call that correlation is equal to, okay, let's call that correlation is equal to the log transformation of sales and the fuel efficiency. Okay, now let's try running this data set here. Okay, error in split data. This correlation could not find function. Okay, we are splitting this data past the pipe function we group by time. Trying to make this split data. Let's see. And run this all over again. Okay, now running that all over again, we've already splitted the data set. We can see we splitted the data set into two. That gives us the two. Now we can see the correlation is 0.238 and 0.13 as what we got before. That is what we got. That's the correlation. But if we want to retrieve the correlation results, we can use the split underscore data. Okay, can use split underscore data and we produce the dollar sign. I'll bring this correlation and we'll bring in this one. Let's try running this and see. That gives us for the first estimate. And we'll run this also. We'll run this. It gives us that for the second estimate. That gives us for the second estimate. Now, that is what we got here. Split data. Now you can see that the values what we got are similar. Okay, now that is now you can see this value we got here and the value we got here is different with what we have using the SPSS. Look at what we're going to say 0.45 and 0.203. Okay, now we can compute the correlation coefficient and the test result based on the split dataset. Okay, we could also copy this. And test for the correlation coefficient. That one we're going to use, but this time around, let's try to differentiate it. Let's see correlation test. Let's call that correlation test. Then what we're going to do here is the correlation dot test. But before then, we are going to use the list function. The list function equals to let's run this and see. Okay, now we run that list data. Now if there's a split data, let's call the split data test. Let's make this split data test. Let's try differentiate it. Okay, we already have split dataset. Let's make it this and run this. Now when we on the split data test and we have this. Now you can see this is what the gift we are getting. So we can also use this method to retrieve the results. But this time around we're going to use the split underscore test. And we have correlation test here. So we copy this. I will make this to be 2. So now let's run this. That gives us the correlation test. Now we can see we still got the same correlation test with what we got there. But this is quite different with what we have using the SPSS. Now using the SPSS we have 0.451 and we have the 0.203. So how can we get what we got to SPSS? Now let's split this data set using another method in splitting this data set. So this time around we call that split. Let's say split data underscore A. Okay, let's call that split data underscore A equals to. Okay, let's see the data we want to split. Let's pass the okay, let's split the data set using another method in splitting our data set. Okay, we've seen the first way of we see a particular method in splitting our data set. Let's use another method in splitting the data set and let's compare the output with what we have in SPSS. Now let's call this car sales. We are splitting the data set now. So let's call that car sales 7. Okay, car sales 7 split A. Okay, equals to. Now we bring up the car sales dataset. Now let's bring up the car sales dataset. Then we are going to pass the pipe function. Pipe function will act as a chain. Then we use that to filter this particular dataset. Sorry, I want to see the filter that I'm picking. Okay. We are going to use to filter this dataset. We are going to filter the type. Then we are going to use to save this as the B, and we are going to make this 1. Okay, we are going to run this data set here. Could not find function. But let's quickly activate that. Okay, fine. It's also part of a deployer function. It's also part of the statistics package. Okay, so I've activated that function. So if you don't have that package installed in your R Studio, you need to install the package and you activate that particular package. My system went down. Went down, and I lost the dataset. I lost everything I was doing initially on R Studio, so I just have to run down all over again. Now it's telling me car sales 7 is not found. Now, so just as I said earlier on that my system shut down and I lost all that I was doing. So I have to do all this all over again. So just as I said earlier on, my laptop shut down and I have to activate all this all over again. So you don't need to do this, but I have to do it because my system went off. So my system went off. I have to repeat all the steps again. So okay, I have to come here to repeat all the steps before going down there. Okay, now I think I should be able to work on this now. Okay, let me see. I shouldn't have a problem with this now. Okay, fine. Now that splits the dataset into two. Um, you can see the first part of the dataset, CASI 7, split dataset A. We can see that we have 115 observation. For the B, we have 41 observation. But that for the CASI 7, the number of observation is 156 observation. That is the total observation. So for the split data sets, we click on that. That gives me the number of data sets. Now you can see the type is all 0. That gives me the data set for the type. That is all 0. Okay, that is all 0. Then for this order, for the B part, I have only 41 data sets. For the B part, I only have the 41 data sets, and you can see the type is 1. Now let's select our variable of interest. Now in selecting a variable of interest, we are going to use the car sales 7a. We're going to introduce a pipe function and we use the select function. Now I'm interested in the MPG. Okay, the sales data and then okay, as well. Okay, now you can see that the data sets I have now is only have 3 datasets now. Compared with what I have here, that I have more than three variables. Now I've selected my variable of interest. So those are the those are the variables that I'm interested in. So we can simply copy this and run this. And we make this to be B. We run this. Now running this, we also have 3 variables. Now you can see the first one represent those with type 0, that is for automobile. This first data set that represents automobile. Then the second data set represents the truck. Okay. Now in our data set, we have the automobile and the truck. These are the two automobile. These are the two data sets we have. Those are the two data sets we have. So we have automobile and we have the truck. Those are the two data sets that we have. Okay, now we've gotten that. Now we can now save this particular data set. Now we can decide to save, we can save this data set in an object. So we're going to save this data set in an object. Let's call that car sales 8. Or let's say we're talking about car sales. That is a split data set. So car sales 7 split A. We can also call it since it's a split data set, we can call it car sales sub-split. Okay, let's just use the sub-split. Okay, let's say car sales sub A. I think that would be better. Or let's say car sales split. Let's use the sub A. I think that will be better. Okay, now that is fine. Then we are going to call this. Okay. Now we call that car sales underscore sub A. That's for the first split. And then we can call this as well. Okay, fine. We have this. Okay, this will be the B. So we can simply run this line, these two lines of code. Let me run the two lines of code simultaneously. Now I have the sub. Now we can now see just the three variables of just only the three variables we're interested in. I could likewise I do this, and that gives me just only the three variables we are interested in. Then let's filter our data set for non-zero value. Now, when you look at the sub, you can see we have zero. So there are some zero value in the fuel efficiency represented by the MPG. So we are going to filter this data set. We are going to filter that data set now, and we have the car sales sub A. Now we're going to pass the pipe function. We're going to pass the pipe function, and we're going to use now this time around we're going to use the filter function. We are going to filter our data set now. And we selected this. Now we want to filter this data set. Now we're going to call this a different name. Let's just call it we should we call it A. Let's just call it split A. Let's call that split A is equals to filter. We're going to filter that data set using the car sales sub A. Now, this is a class sales sub A. We've saved this in an object known as class sales sub A. Then we want to get MPG that is greater than 0. Okay. Then we're going to run this. Run that line of code. Okay. Then that's run the line of code for split A. Now you have 113 variables. Initially we have for the sub A. For the sub A, the number of data we have is 115 observation. 115 observation for the sub A. Now we have currently we have for the split A. Currently we have 113 data sets in the split A. So when we click on this, that we can see that the 0 is no longer there. Every 0 value has been deleted from this particular dataset. We do that for B, and we can see that for split B. Sorry. I have a little problem with my cursor. Okay, let's run this line of code afresh. Okay, and then let's run this other line of code. But that will be B. Okay, now running this line of code, that reduces that to 41 variable. Initially, the split B reduces to 40 variable. Initially, I have the number of variables were 41. Now, initially, the number of variables were 41. So that reduces the variable and that drops the rows that are 0. So what we did was we dropped the rows that are 0 in our data set. Now you can see that initially we have the 0, but the very moment we drop that, my cursor is giving me issue here. The moment we drop that row, the moment we dropped the row for the B, we no longer have the 0 value being displayed. Okay, and let me. Okay, now we've done that. Now what we are going to do, we are going to compute the correlation coefficients. Now we use the correlation function, and we have the split A. Okay, we are going to use the split A, and we introduce the dollar sign, the MPG, comma, the split A, the dollar sign, and we introduce the log of sales. Okay, we run this, and that gives us the correlation of 0.50, which is similar with what we got using the SPSS. I'm going to go back to SPSS. My system was shut down, and I'm going to go back to that. We're going to compare the values with what we got in SPSS. Okay, running this line of code as well, that gives me an approximately correlation coefficient of 0.20. So that's to tell you that the relationship correlation between fuel efficiency and the sales of vehicle for the automobile and that for the truck are both positive. But let's check if they are both significant. Okay, all what you need to do is to just copy these two lines of code and paste it here, and we can simply use that to check for the significance. Now you can see that for the automobile is significant. That means there is a significant relationship between the sales of automobile vehicle and the fuel efficiency of such vehicles. As such, car manufacturer or the design engineer should focus on the efficiency of automobile vehicle while producing a vehicle because it influences the sales of the vehicle. But in respect to truck, now we can see that for truck that the p-value indicates that is not significant. As such, in producing trucks, the design engineer shouldn't focus on the efficiency of the truck because it's not considered by the customers, by those who buy truck or by those who purchases truck when buying the truck. Now we can look at the Spearman correlation coefficients. Now let's copy that. Let's copy those two lines of code. Now I'll compute this the Pearson correlation coefficients. Now if we want that for the Spearman, we have to use the method. Okay, we have to use the method. You use the double quote the Spearman. So we are going to do that for both data sets. We're going to do that for both data sets. Okay, now let's run this for the first data set. It's getting us Q that it cannot compute the p-value because of ties. Now, because of ties, the p-value cannot be computed. Now, the p-value cannot be computed because of the ties, but nevertheless, it computed the p-value. That tells us that there might be an error in this computed p-value by R Studio because we were already told that because there is warning message p-value might not be computed. So nevertheless, the real p statistics was computed. Now, based on the real p statistics of 0.42 or approximately 0.43, it tells us that there's a positive relationship between fuel efficiency and sales of automobile. But nevertheless, the p-value already gives us that is significant, but we have to take that with a pinch of salt, because the p statistics might include some error. Now we've computed that for now. We can see that we got that for the real value telling us it's positive, but also as well is not significant. So it's telling us that it's not significant. Using the Spearman and the Pearson correlation coefficients, we reached the same result, that the relationship between car efficiency, the relationship between the efficiency of efficiency of the vehicle and the sales for that of automobile is significant, and that of the automobile is significant, and that of the truck is not significant. So we can simply copy that, and we can use the candle. Now, all what we need to do, we just change that to candle. We all in small letters. We can simply copy that, and we move to this. Okay, we'll paste there. Now we can see we have the candle. Now we could also use this method. We can say C. If we don't want to just use only the double quotes, we could put that in a bracket. That could be done in a bracket. Okay, we're going to run this line of code. Now, using the candle, let's see what will be our output. Now, using the candle, it computed the p statistics perfectly, but the real statistics telling us that we have a correlation of approximately 7.31, which is positively but not a strong positively correlated coefficient. But nevertheless, it is significant. It's telling us that it's significant. There's a positive correlation between the fuel efficiency of automobile vehicle and the sales of the vehicle. Then using that for the truck, to check for that of the truck, we can see it's giving us an error message that the truck statistics, that the p-value statistics, there might be an error in the p-value statistics, but nevertheless, it's telling us that it's not significant and the relationship is positive. We arrive at similar conclusion with our results for the Pearson and our result for the Spearman correlation coefficient when we test the correlation coefficients. Now, can see either method gives us the same thing. Now, we could also look at the sales. Now, this is using the logarithm value for sales. Now, let's try just using that for the sales, and let's see. Instead of the logarithm value, let's just use that for the sales for Spearman and then for Kendall. Okay. Okay, now let's go up. Okay, for the Spearman, okay, let me simply copy that because my mouse pointer is behaving funny. It's being funny. Okay, now that's for the Spearman. Now let's run this line of code. Now running this line of code, now you can see running this particular line of code, it gives us similar thing but with an error there. Now you can see the Spearman correlation coefficient, the real, is giving us 0.42 for that experiment, and then for the ordinary sales, and that of Kenda, we have this value. Okay, now let's compare for the original sales, that's for the original sales and that of the logarithm value of sales for Spearman. Now you can see we have 0.425074. That's for Spearman for automobile. And let's go to Spearman for sales. Now this is without the logarithm value. Now you can see we got the same value. Now we'll make use of the logarithm sales value for the first one, and now you can see we make use of the logarithm value, and here we used the sales without the logarithm value, and we arrived at the same result. Why? Now the reason is this: the Spearman and Kendall correlation coefficients compute the rank association between your variables. It computes the rank association between your variables. That is what it does. It computes the rank association between your variables. So it's not affected by the log transformation of your dataset. Now, when using the Pearson correlation analysis, the very moment your dataset violates the parametric assumption, especially that of normality of the dataset, it is advisable to use other correlation coefficients and not to use the Pearson. Or rather, if you want to use the Pearson with that particular data set, you have to introduce a transformation method. You have to transform your data set so that it could be normally distributed. Once it's normally distributed, then you can go ahead and use the Pearson correlation coefficient. It will give you a better estimate of your data set. It will give you good statistics, to give you the best statistics for your data set. Now, but when the dataset is not normally distributed, it violates the parametric assumption, then it is advised we use either the Spearman or the Candel correlation coefficients. Now you can see that using that for it gives us similar results. Now let's try using this for. Now take note that the sales is not the logarithm sales for Spearman for the truck. Now you can see we have approximately 0.23 as well as 0.24. Now let's use that here for the with this. Now you can see we are using the logarithm value for the sales. We have similar value, approximately 0.24. Now because the rank correlation coefficient of Spearman and that of Candel is not affected, it's not influenced, it's not affected and is not influenced by the logarithm transformation of our dataset. So we could also try that for the Candel. We could try that for Candel for the automobile, and we compare that with approximately 0.1, and we compare that with the non-logarithm transformation, and this is what we have here, and we run that here. You can see we have similar results. So we can also compare that 0.16, approximately 0.16. That's for Candel with the sales. But now we're going to look at it with the logarithm transformation. That gives us similar value. Now we're going to compare this value we get. We're going to compare our output we just gotten with that of SPSS. We're going to see, we're going to compare that with SPSS. Now let's look at the SPSS. Let's run our output on the SPSS. Let's run our analysis on the SPSS, and we're going to compare the result again with that of R Studio. So let's run the analysis afresh on SPSS. We are going to run the analysis afresh on SPSS. Now this is a dataset of SPSS, and we're going to split the datasets. Now, so splitting the dataset, we click on that and we go to. First and foremost, let's go to the select case. Recall we worked on this. I have to repeat this process all over again. You don't need to repeat this process because my system actually shut down. My system actually went off. So I have to repeat all this process all over again. So I'm going to quickly repeat that and come to the stage, to the point where we were before my system went off. Okay, now I'm going to click on continue. I'm going to click on OK. Now that removed the metro dataset. Then we did the select cases. So then we split our data set. Okay, we use the compare, and we make use of the motor vehicle, and we click on OK. Okay, fine. Now that split our dataset into two. Then we went to analysis, and we go to the correlate and the bivariate correlation. Then we run the correlation for the sales and the fuel efficiency represented by MPG, and the log transformation of a sales dataset. Now we run this, and we use the Pearson, but this time around we want to compare. Okay, let's use the Pearson image first and foremost. Now you can see that SPSS gave us a correlation value between the fuel efficiency of automobile vehicle and the sales of automobile vehicle. When we use the logarithm transformation, we have a correlation of approximately 0.45 or 0.451, and we can see that it is quite significant because we have this at 1% level of significance. That's for the automobile. And when we go to R Studio, we can see that for the Pearson, when we run the correlation of a split dataset, we'll make use of this other method of split dataset. We'll make use of this other method of splitting our dataset. We run our correlation coefficients. And we saw that that gives us a correlation of 0.450, similar with what we got in SPSS. So when we run that for truck, we have 0.20. Then when we look at that, approximately 0.20, but not significant. So also we want to test the significance of that. What we did was to run the correlation test, and we saw that the p-value, it was significant. Then for the truck, we test the significant value is not significant, and which is similar to what we got using the SPSS. Now you can see using the SPSS we have 0.210. Okay, 210. So we come to this, and we can see we have a p-value of 0.210. Well, that might be a coincidence working that, and then we have through the automobile, we have a p-value of a c-value of 0.0000, and the rest of them. Okay, now that is that. Then when we go to the R Studio, after that we now run. After that we run the correlation test for the Spearman and that of Kendall. We run that for Spearman and we run that for Kendall. So let's go back to our SPSS. Let's recall the bivariate correlations box, and we are going to run that for Spearman and the Kendall. That's the Kendall TOA B statistics and the Spearman. Now for the automobile, looking at the Kendall, we have 0.310 about, and is significant at 0% for Kendall. So let's compare that with the results we have using the R statistics. My mouse pointer is still giving me a little bit of issue. Now using for Kendall, for the automobile, we run this. We can see we have approximately 0.31, and also it's significant, which is similar with what we had in SPSS. So for the truck, we compare this value together. Now for the truck, it gives us approximately 0.16, and we are told that the p-value is was unable to be computed accurately. So we look at that for SPSS for the truck. Now for the candle for the truck 0.1, and we can see the p-value of significant value of 0.163, which is actually similar with what we got here in this. Okay, now then we now look at the Spearman correlation coefficients. Now look at the Spearman correlation coefficients. Running the Spearman correlation coefficient. Running the Spearman correlation coefficient for the sales variable without introducing the log transformation of the dataset. My mouse pointer is just giving me this kind of headache. Now we can see we have approximately 0.4250. Now that is using the Spearman. Now using the Spearman correlation coefficient, Now for that of the sales, but not introducing the logarithm transformation, we introduce the Spearman there. Now we can see Spearman, we have similar results with what we got in SPSS, and it's significant, but for that of the truck is 0.159, 0.237 for Spearman, and we have a significant value of 0.141. So let's look at that for the truck and let's compare that. Now you can see this is quite similar with what we got in the SPSS. Okay, that's similar with output in SPSS 0.141 significant value, and here we have approximately 0.141 p value. Okay, now despite okay, now we also look at the sales. Now we can also look for the sales for the sales. We have just included the sales. Now for the sales, now let's go to R Studio. Now for the sales post payment, we have for this last one for truck, we have 0.237 for the sales without introducing logarithm transformation. Now going to our SPSS for payment for the sales, we looked at that for payment for the sales. Okay, payment for the sales without increasing logarithm x, we have 0.425, and let's see what we got here. Okay, that's the payment for the sales. The payment for sales 0.237, using the payment for the sales 0.237, and that is for the truck. That is for truck 0.237 for the payment for sales without using the logarithm transformation. Then we go to our statistics for the payment for the sales without the logarithm transformation. We have 0.2, approximately 0.3 and 0.43, and that's the same thing we have here for the automobile, approximately 0.43. Okay, and it's significant, which is similar with what we got in located is significant. That is quite similar with what we got in SPSS. Okay, now you can see comparing. Let's look at that of Candle. Candle for just the sales for automobile, we have that 0.31, that is for the Candle for the automobile. Now you can see Candle for the automobile approximately 0.310. Okay, that is that and is significant. But for the truck for Candle, you can see we have the sales 0.159 and is not significant. So we come to this and we run that here. Now you can see we arrived at a similar result. We got similar result using both the SPSS and we're using both the SPSS and the R Studio. So while running analyzing your dataset, once the dataset validates the normality assumption of the parametric dataset, it's best to use a Spearman. Once you validate it, it's best to use the Kendall or the Spearman correlation coefficient. But if you want to use the Pearson correlation coefficient with such particular dataset, you need to apply a logarithm transformation to your dataset. The question here: why going through the stress of applying logarithm transformation to your dataset when you can easily use a Kendall or Spearman to analyze your datasets, to analyze the association between your variables? Since the Kendall and the Spearman does not take into consideration whether the dataset is normally distributed or not, it doesn't care, it doesn't bother. But if the data is distributed or the data is not distributed, it gives the same result, the same output. So why going the stress of using a Pearson and transforming your data sets to use a Pearson correlation coefficient? Now, the reason is this: you can use Kendall and Spearman to check, to detect the existence of association within your dataset, because the Spearman and the Kendall gives a rank association within your dataset. Once you detected that there's an association within your dataset, then you can use Spearman to determine the strength of the association within your dataset. Spearman is going to give you a very better estimate, but under a normal distributed dataset. So once your dataset is not normally distributed and you detected by using the Spearman or Kendall that there is an association within your dataset, then what you need to do is to transform the dataset if the dataset is not normally distributed and use the Pearson correlation coefficient. So yeah, we conclude that for automobile vehicle, there is a correlation between the sales of automobile vehicle and the fuel efficiency of the vehicle. But for truck, there is no correlation. There is a correlation, but the correlation is positive, but it's not significant. As such, the design engineers need not to focus on efficiency of truck while producing trucks, but for that of automobile, they need to focus on the efficiency of the use of fuel while producing automobile vehicle.